Good morning, and thank you for having the opportunity to talk to you. My name is Peter Ramberg, and I am a historian of chemistry, historian of science at Truman State University in Crooksville, Missouri. If you're wondering where that is, I'll explain in just a moment very briefly. My interest has been in 19th century organic chemistry. My first research project was in the history of stereochemistry and the origins of stereochemistry. And organic chemistry in the 19th century. But I broadened out since then. I've been part of this large project that Peter started on the Bloomsbury Cultural History of Chemistry. So I was the volume editor for the 19th century, so the fifth volume 5. And so that's been a project for the last 5 years or so, just appeared this year. And what I'm talking about today is kind of a summary of my introduction to the volume, which is a fairly lengthy description of 19th century chemistry. So just briefly, for those of you, why is it not? There we go. For those of you who don't know your US geography, here's the United States, there's Chicago and New York. I'm in Missouri, which is right in the middle. And here's Missouri, and then the red circle is around Crooksville. So you can see here I'm midway between St. Louis and Kansas City. Just for those of you who don't know, not many people in the US know where we are. So I usually have to explain where Truman State University is. It's named after our former president because he was from Independence, Missouri, here in Kansas City. Okay, so with that, let me get started. My topic here is, go back briefly, is just training, theory, and industry. I've shifted the order a little bit from the original title. And one of my main themes is creating modern chemistry in the 19th century. And I think I'll give you an overview of why I think this is the case. On March 11th in 1890, chemists at a special meeting of the German Chemical Society gathered for an elaborate banquet in Berlin. The guest of honor was August Kekule, who 25 years earlier had suggested that the chemical structure of benzene was a ring of 6 carbon atoms, a theory that had proven to be an extraordinarily productive tool for organic chemists. Guests were treated to a 9-course meal, numerous toasts, congratulatory speeches that lauded the success of Kekule's theory. In one of the toasts, August Wilhelm von Hofmann, on the right, proclaimed that in the time since Kekule proposed the ring structure, organic chemistry had metaphorically grown from a small, shallow creek into a, quote, deep and mighty river across which one could scarcely even see. And Kekule's benzene formula provided the soil, quote, soil from which, to our astonishment, we saw the organic chemistry with which we were familiar grow tall anew. While Hoffman and the other speakers at the banquet might have been understandably prone to exaggeration and self-congratulation, they knew firsthand that organic chemistry had grown spectacularly since the 1860s due to the success of the structural theory of organic chemistry. Kekule had first elaborated the outlines of the structural theory in the late 1850s and used it to develop his benzene theory. By the 1860s, chemists quickly realized the strength of the structural theory for bringing order to the thousands of known organic compounds and predicting still more compounds. In the world of 19th century chemical theory, the late 1850s would be the crucial turning point, or a quiet revolution, when most chemists quickly united behind a single vision of the molecular world. The emergence of structural theory of chemistry during the 1860s, like the appearance of evolution in biology and electromagnetic theory in physics, was one of the great intellectual accomplishments of 19th century science, and a central component in the explosive growth of chemistry during the 19th century as a science, as a profession, and as an industry. A chemist from 1815 transported to 1914 might recognize the general outlines of chemical theory and practice in 1914, but they'd be likely astounded by the changes. The number of practicing chemists had dramatically increased, and the vast majority of these chemists were now trained professionally as chemists, publishing articles in journals devoted exclusively to chemistry or to a subdiscipline of chemistry. The number of new chemical compounds had increased exponentially, and the commercial wealth generated by chemical industry was equally staggering. Universities in all industrialized countries had large buildings devoted to chemical teaching and research, and large chemical firms had laboratories dedicated to chemical research and development. Today, I'm going to briefly outline these major changes in chemical practice, changes in theory, creation and spread of a new means of training chemists, and the appearance of a new science-based industry. So let's take each one in turn. This is, as I just meant, this is an extremely broad overview. And so there's very kind of skimming the surface of these developments. So we'll start with training and the emergence of the teaching research laboratory, as I call it. Chemists had long been trained by direct instruction in the laboratory in a master-apprentice relationship, but until the 19th century, this transmission of chemical knowledge and practice had remained at a relatively small scale. The enormous increase of chemists during the 19th century can be attributed to the success of the chemical teaching research laboratory at German universities in the decades after the 1830s. The origins of the teaching research laboratory lay in the early 19th century, when officials in both France and the German states, and later Britain, showed a new interest in public health, including water purity, food adulteration, and most importantly, the quality of medicines produced in an expanding pharmaceutical marketplace. These reforms led to the training of pharmacists that required specific examinations on the chemical analysis of medicines. In response to these reforms, a number of private chemical pharmaceutical institutes were founded in the German states for training chemists in analytical techniques. One of the earliest of these private institutes was founded in Prussia by Johann Tromsdorf in 1795, where he trained students closely in drug preparation and analytical techniques using lectures and close laboratory instruction. Among the earliest laboratories at universities was run by Friedrich Strohmeyer in Göttingen, who had already begun teaching optional courses in analytical techniques in 1810 as part of the medical faculty. By the 1820s, Strohmeyer was attracting hundreds of students from all over Germany, training them as pharmacists, physicians, agronomists, mineralogists, mining officials, and many of the next generation of university professors. Although Strohmeyer was certainly among the first chemists to introduce regular laboratory instruction at a university chemistry laboratory, his laboratory would soon be eclipsed by Justus Liebig's laboratory at the University of Gießen during the 1830s. Liebig had arrived in Gießen in 1824 after 2 years in Paris, where he had learned sophisticated analytical techniques with Joseph Louis Gay-Lussac. Liebig attempted to create a pharmaceutical chemical institute similar to Tromsdorf's, and initially ran his institute privately because chemistry was not generally regarded as sufficiently scholarly for a university. Liebig initially had few students, and his own research lacked focus and originality, in part because of a lack of specialized equipment that he'd used in Paris. Liebig's fortunes would change in 1830 after he turned to organic chemistry and invented a new apparatus, this is on the right here, for the elemental analysis of organic compounds that produced results equal in accuracy to previous methods, but was so simple that even his students could learn the technique very quickly. The Kaliapparat, as it was called, the potassium hydroxide apparatus, enabled the growth of Liebig's laboratory during the 1830s. Gießen would become the destination for many aspiring chemists from around the world who wanted to learn the new techniques. By the 1840s, Liebig had as many as 68 students in the laboratory, with a significant number of advanced students engaged in coordinated research projects. The Liebig model quickly spread to other German universities, but the early German laboratories were often modest, housed in small repurposed buildings that quickly filled the capacity. The cost of running the laboratories was also was high, and the laboratory budgets were not sufficient to cover the total cost of running the laboratory. This began to change by the 1860s when the German states, spurred by crop failures and Liebig's vigorous promotion of applied chemistry, began building large, expensive chemical institutes to foster chemical research, accommodate the influx of students, and attract prominent faculty. The state took on more costs of running the laboratory, and the number of faculty increased. These large second-generation institutes, in turn, became inadequate by the 1890s, as chemistry became increasingly fragmented into subdisciplines of inorganic, physical, biological, and radiochemistry, with increasingly divergent methods and aims, requiring the construction of even larger institutes. In France, Jean-Baptiste Dumas and other chemists adopted the Kaliapparat, but found it difficult to replicate Liebig's teaching research model. Dumas pleaded with authorities to help recreate the conditions of Liebig's Gießen laboratory in Paris, and later generations of chemists made similar appeals without success. In Great Britain, Liebig's visits between 1837 and 1844 contributed to a growing perception that Liebig's laboratory, with its practical applications of chemistry, had made Germans superior in agriculture and industry. This inspired the creation of new chemical teaching laboratories, including the Royal College of Chemistry in 1845, with the support of Prince Albert, and headed by Liebig's hand-picked student, August Wilhelm Hofmann. In the United States, Evan Horsford returned from Liebig's laboratory to Harvard in 1847 to create a new institute. but high construction costs and the difficulty of acquiring state-of-the-art equipment meant that there were insufficient resources to adequately build and maintain the facility. In 1876, Ira Remsen would establish a more successful research laboratory at the Johns Hopkins University, but by the 1890s, Remsen's research and laboratory had become dated. This is Liebig's laboratory, okay, and this is Remsen. Remsen's laboratory had become dated, replaced by far more dynamic and productive laboratories at other American universities dominated by physical chemists. And we'll see more about that later. Chemical training would also make its way to St. Petersburg in Russia during the 1860s by a contingent of younger chemists returning from studying in Germany. As part of its westernization process, Japan brought in foreigners to set up and direct chemical instruction at Tokyo University and the Imperial College of Engineering. And by the late 19th century, Western-style chemical instruction had become firmly established in Japan. So the first part of this is just about the establishment of this, the idea of the teaching research laboratory for preparing large numbers of students in chemistry. Okay, so let's move on to theory. By the early 19th century, chemists have developed three primary and interrelated goals. First, to determine the elemental composition of substances using Antoine Lavoisier's system from the late 18th century. Second, to use Dalton's atomic theory to establish atomic weights for the known elements and determine the proportion by weight of each element in pure substances. And third, to express those proportions in formulas of some kind. The Swedish chemist Jakob Berzelius, one of the earliest champions of Daltonian atomism, set the theoretical framework for reaching each of these three goals. The discovery of current electricity and its early application to chemistry suggested to Berzelius and others that chemical affinity must be electrical in nature. When exposed to electrical current, the elements that made up compounds would collect at either the positive or negative pole of a battery, and Berzelius suggested that each element was either electronegative or electropositive. Compounds would therefore consist of a positively charged piece and a negatively charged piece held together by the forces of electrostatic attraction, a theory that became known as electrochemical dualism. This composition could then be expressed in chemical formulas using a new notation that Berzelius introduced in 1814, still used in slightly modified form today, that represents atoms with letters and the proportions of atoms by superscript numbers. Today it's subscripts. By 1815, Daltonian atomism had already made significant headway among European chemists as a method for ascertaining chemical formulas. There was no doubt that Dalton's main idea that elements combined together in fixed weight proportions was true, but there were two ways of interpreting Dalton's theory. The first interpretation, physical atomism, held by Dalton himself, Thomas Thomson, and Berzelius, assumed that these proportions were caused by the weights of the different atoms themselves, solid spheres that had the same relative weights as the macroscopic weight ratios. Under the second interpretation, chemical atomism, chemists assumed that Dalton's weight ratios were correct and useful, but made no claims about the physical nature of the atoms themselves. While chemists remained divided about physical atoms throughout the century, all chemists adhered to various versions of chemical atomism. Many chemists rejected physical atoms on methodological and metaphysical grounds because they found no compelling reason to assume that the cause of the combining proportions was the weight of the atoms themselves. Humphrey Davy wrote that Dalton was, quote, too much of an atomic philosopher and has often indulged in vain speculation. The essential and truly useful part of his doctrine, the expression of quantities in which bodies combine, is perfectly independent of any views respecting the ultimate nature either of matter or its elements. Davy was convinced the actual number of elements must be much smaller than the long list begun by Lavoisier and used by Dalton. He thought there should be only perhaps 2 or 3 elements. William Prout went even further and suggested that because Dalton's weights were dominated almost completely by whole numbers, hydrogen as the lightest element must be the only true element. And each of Dalton's elemental atomic weights was an integral multiple of the hydrogen atom. Prout's hypothesis, as it came to be known, would hover in the back of chemists' minds throughout the 19th century, although more accurate atomic weight measurements indicated that some elements, like chlorine, had weights almost directly between 2 integers. By 1820, chemists throughout Europe had come to embrace chemical atomism as a tool for constructing chemical formulas, but competing systems of equivalent and atomic weights led to different formulas. By mid-century, the result was many different but internally consistent sets of atomic weights across Europe. This led to many different possible formulas for the same compound, depending upon which version of atomic weights was being assumed. So in the first part of his textbook, published in 1859, for example, Kekule listed 16 different formulas for acetic acid. I've got them here on this slide. And these are all calculated or formulated based on differing atomic weights and different ways of expressing acetic acid. The key for resolving this problem had already been suggested in 1811 by Emilio Avogadro. The competing systems of atomic weights could be collapsed into a single system if chemists assumed that individual particles of the most common gases, hydrogen, oxygen, and nitrogen, consisted of two atoms. At the time, Avogadro's hypothesis was ignored, primarily because it was difficult to understand how two atoms with the same electronegativity, as both atoms of hydrogen would be positive, could bond with each other. Avogadro's hypothesis would soon be revived by Stanislaw Cannizzaro at the Karlsruhe Congress of 1860, one of the first international conferences in the sciences. Cannizzaro had distributed a pamphlet there based on his own attempts to organize and present atomic weights to his students. They explained how Avogadro's hypothesis would lead to a consistent set of atomic weights, and then most chemists were soon united behind the single set of atomic weights based on Cannizzaro's pamphlet, not at Karlsruhe, but afterwards. The final agreement on atomic weights during the 1860s would eventually lead to the periodic law and the periodic table. Chemists had already long recognized the repetition of certain chemical properties among groups of elements. And what would later become the periodic law was also noted in several ways in the 1860s by, among others, John Newlands, Gustav Henrichs, and Lothar Meyer. The most lasting statement of the periodic law would come from Dmitry Mendeleev in 1869, as a result of writing one of the first original Russian language multi-volume general chemistry textbooks. Motivated by contractual operations to finish the second volume of the text as quickly as possible and seeking an effective pedagogical tool, Mendeleev settled on using atomic weights as the one true defining constant for each element. When he ordered the elements according to their weight, the regularities and valence and properties noted by earlier chemists became clear, and he arranged all the elements into a table to express this periodic law. Mendeleev's insistence on the primacy of atomic weights allowed him for the first time to make bold predictions about not only the existence of new elements, but also their atomic weights, densities, and valences. His insistence on the validity of the periodic law also compelled him to argue that a few atomic weights had been incorrectly measured. The eventual success and widespread adoption of the periodic table resulted from the isolation of the predicted elements and the discovery that their properties were close to Mendeleev's predictions. It briefly met some difficulties in the 1890s when William Ramsay and John William Strutt, or Lord Rayleigh, announced the isolation of chemically inert gases that did not fit within the existing table. In 1898, Ramsay argued convincingly, using the periodic law, that the new gases belonged in a new column on the periodic table, the noble gases. Despite the success of the atomic theory in bringing order to chemical phenomena, and despite the final agreement on atomic weights, there remained skepticism and debate about the existence of physical atoms up to the end of the century. In Britain, Benjamin Brodie was extremely skeptical of the speculative mechanical picture of molecules given by drawings of molecules on paper or by models of balls and what made of balls and wires. Edward Franklin and Alexander Williamson were reluctant to commit to physical atoms, but vigorously defended the utility of molecular models or paper drawings as heuristic devices. The extraordinary success of the atomic theory since Dalton, argued Williamson, led, quote, inexorably to the conclusion that matter consists of chemical atoms, unquote, but said nothing about, quote, whether the elementary atoms are in their nature indivisible, or whether they are built up of smaller particles, unquote. In France, Adolphe Wurtz was nearly alone in strongly supporting and defending the atomic theory against many influential French skeptics of physical atoms. These skeptics were led by Marcellin Berthelot, who exerted a strong influence on French science, particularly after Wurtz's death in 1884, hindering atomistic ideas in French higher education. Berthelot wanted chemistry to be independent of physics and free of unnecessary hypotheses, including physical atomism. Berthelot's goal was aided by the prominent views in France of Henri Poincaré and Pierre Duhem, who advocated a conventionalism in which the actual existence of physical atoms was deemed unnecessary for the success of science. In Germany, the atomic debates came to a head at the 1895 meeting of the German Society of Naturalists and Physicians. The physicist Georg Helm, and he's anonymous here because I've been unable to find a portrait. So he is the Facebook anonymous portrait here. Physicist Georg Helm and the chemist Wilhelm Ostwald both advocated an anti-atomistic, energetic worldview, in which matter was, quote, imaginary, an entity that we have rather imperfectly constructed to represent that which persists through the flux of appearances, unquote. Both physicists and chemists at the meeting argued strongly against Helm and Ostwald's energeticism, invoking both the kinetic theory of gases and the well-established existence of stoichiometric laws. The latter were clearly the weakness in the energeticist viewpoint, and like Berthelot, even Ostwald had accepted chemical atomism. The Liebig conference, this conference failed to reach any kind of consensus, but within the next 10 years, the discovery of X-rays, the electron, subatomic structure, and finally, Albert Einstein's 1905 paper explaining Brownian motion would eventually convince everyone, even Ostwald, of the viability of physical as well as chemical atomism. Okay, so next part of theory is the rise of organic chemistry. So organic chemistry, as contrasted with mineral chemistry, originally referred to the chemistry of substances derived more or less directly from plants and animals, including the roles of those substances in plant and animal physiology and anatomy. This original conception of organic chemistry was transformed radically in the 1830s into an entirely different science. Interest in the origin of organic compounds was de-emphasized in favor of studying their reactivity as chemicals. As the chemistry of these compounds became more understood, the number of artificial compounds increased exponentially. In 1800, chemists knew only a few dozen organic compounds, but around 1820, this number began to climb steadily, doubling roughly every 13 years. Already by the 1830s, the artificial organic compounds outnumbered the natural ones, and by the 1840s, chemists explicitly redefined organic chemistry to mean the chemistry of all compounds containing carbon, whether natural or artificial. Further complicating matters, all of these compounds consisted of only a few elements, mostly carbon, hydrogen, oxygen, and nitrogen. Between 1815 and 1830, Berzelius organized the basic theoretical framework for bringing order to the growing number of organic compounds. First, Berzelius was convinced of the unity of chemical laws, that organic and inorganic compounds alike should follow Dalton's laws of definite proportions. The proportions in organic compounds were more complex than those in inorganic compounds, but that complexity could be understood by assuming that formulas for organic compounds could be found by drawing analogies to better known inorganic compounds. Second, in 1830, Berzelius introduced the concept of isomerism to explain the numerous compounds that had identical elemental compositions, but different chemical properties. When even more such pairs of compounds began to be discovered, such as silver fulminate and silver cyanate, urea and ammonium cyanate, tartaric and racemic acid, it became clear that composition by itself could not explain chemical properties. Third, Berzelius suggested the different properties of isomers could be explained by a different arrangement of atoms in molecules. This arrangement would be depicted by rational formulas that would group atoms in different ways to emphasize different parts of the molecule. Each rational formula emphasized a different hypothesis regarding the groupings of the atoms within the molecule. Berzelius's framework for understanding organic compounds proved to be remarkably enduring, as the search for arrangement and rational formulas to explain isomerism drove much of chemical theory throughout the 19th century. Although chemists were in broad agreement that they should express a compound's properties by rational formulas that depicted the arrangement of atoms, they did not all agree about what the best rational formula might be. Now, I can't go into details here, but there were two major approaches. The first in Germany focused on ascertaining a single formula for each compound, based on the principles of electrochemical dualism. The second, centered in France, emphasized arrangement as expressing the fundamental chemical property or type of a compound. The implications of the type theory were unacceptable to proponents of the radical theory. Under the type theory, if a compound had multiple chemical properties, it could be represented by multiple different rational formulas, depending upon which chemical property was represented. Defenders of the radical theory insisted that each compound should have only a single formula and regarded the putative relativism of the type theory as unacceptable. At the 1890 banquet, Kekule recounted the emergence of these two different approaches to the arrangement by comparing them to two branches of the same river that had diverged in the 1830s. By the 1850s, the travelers on each branch had begun gradually approaching each other, but were still divided by, quote, a thick underbrush of misunderstandings, unquote. Kekule himself had traveled in both branches of this river and was one of the first to realize that the two competing approaches could be combined to form a more productive theory. Kekule's achievement was to combine the alternative visions of rational formulas by insisting that a compound could have only one rational formula, but that formula could be capable of expressing multiple chemical properties. Building on the new concept of valence, that atoms of each element combined with a specified number of atoms, Kekule suggested that each atom in a molecule combined following the rules of valence, and each unique combination corresponding with a unique compound. There could only be one rational formula for each compound, but multiple chemical properties could be expressed simultaneously. The result was the most comprehensive means of reaching Berzelius's original goal, explaining isomerism by the arrangement of atoms in the molecule, where arrangement was how the atoms were connected following the rules of valence. Kekule's theory would prove extraordinarily powerful. It explained existing isomers, enabled prediction of new compounds by simply linking the atoms together by their valence on paper. And as Kekule's theory took hold, chemists would develop further their unique visual language to represent these chemical structures. The most influential, and there's a lot of different representations, but the most influential was created by Alexander Crum Brown in 1864, and it's still used today. Using straight lines radiating from a central atom to depict the valence, the construction of this formula was simple. Using this novel notation, the two known alcohols with a molecular formula C3H8O, for example, could just be represented in these ways. And this, as chemists, you know the difference here. With one alcohol, it has an oxygen atom at the end of the carbon chain, the other has an oxygen in the middle. Crum-Brown's formulas have a particularly modern appearance. And when chemists today look at these formulas, without hesitation, they would say they depict a piece of the microworld, a photographic snapshot of a molecule. Yet chemists at the time were extremely reluctant to give this meaning to formulas. Crum-Brown, for example, was very clear that his notation meant, quote, not the physical, but merely the chemical positions of the atoms, unquote. This qualification about the meaning of chemical formulas is found throughout the chemical literature of the 1860s, making it clear that chemical structures were not meant originally to be literal pictures of the microworld. This interpretation was closely related to chemists' long-standing commitment to chemical as opposed to physical atomism. Despite this epistemological caution, in 1874, J.H. Van't Hoff argued that the structural formulas did represent the physical appearance of molecule in some important ways. In 1848, Louis Pasteur had already noted the association between molecular asymmetry and optical activity. Van't Hoff noted that if a carbon atom had 4 different atoms or molecular groups attached to it in the most symmetrical fashion possible, this tetrahedral array, it would exist in 2 different asymmetric forms, each form being optically active in opposite senses. And this is this here where you can see my arrow, this to the left, is the depiction of that tetrahedral arrangement. Van't Hoff's claim lies squarely within the tradition of organic chemistry of the 19th century. An explicitly spatial arrangement would explain specific cases of isomerism that the structural theory alone could not. The tetrahedral carbon atom proved to be a productive theory, used to explain the isomerism in numerous classes of compounds. A crucial component in the emergence and success of organic chemistry was the development of a unique visual culture that required the ability to switch seamlessly between paper, hand, and imagination. The first of these visual languages was the Berzelian notation that greatly facilitated writing and printing formulas and offered simple algebraic-like representation of organic compounds and allowed chemists to, quote, balance reactions according to the principle of the conservation of weight. Berzelian formulas allowed chemists to discover, quote, by manipulating the formulas on paper, the constitution of the products of a reaction and the radicals within those products. Throughout the 19th century, these paper tools were extended to both graphical representations of bonding in molecules and handheld 3-dimensional models, such as balls and wires or Van't Hoff's cardboard tetrahedra. Chemists developed a sophisticated array of techniques involving visualization of chemical structures on paper in handheld models in their own minds, switching effortlessly between all three. All of these methods allowed chemists to predict the existence of possible new compounds and to suggest ways of making them by analogy to known structurally similar compounds. This plurality of methods and the ability to visualize with pencil, hands, and mind is today, with the addition of computer models, still an essential component of chemical culture and practice. Another factor in the developing culture, this is some of the variety of graphic interpretations of the formulas, including Van 't Hoff tetrahedral models here, cardboard tetrahedral. Another factor in the developing culture of organic chemistry was the multifaceted role played by the synthesis of new compounds. Friedrich Wohler's 1828 accidental synthesis of urea from ammonium cyanate is perhaps the most famous of all syntheses of the 19th century. Because urea was produced by living things, Wohler's synthesis from inorganic materials has been celebrated as the defeat of vitalism. At the time, Wohler and Berzelius both noted the implications of the synthesis for vitalism, but they both already had long been convinced that organic and inorganic compounds should follow the same laws of chemical combination. So artificial urea did not surprise them. Textbooks of organic chemistry were silent on the matter until 1840s, and Wohler, Berzelius, and other chemists primarily saw it as yet another example of isomerism, rather than a synthetic disproof of vitalism. Wohler's synthesis only took on its later significance for vitalism after Wohler's death in 1882, in part because German chemists wished to place the origins of organic chemistry, in which synthesis played a central role, squarely in their own country. Many other syntheses of naturally occurring organic compounds would follow, most prominently acetic acid in 1845, salicylic acid in 1860, and formic acid in 1861. In France, Marcelin Berthelot began a systematic program of intentional synthesis in 1854, making numerous organic compounds from inorganic materials with intensive heat, electrical sparking, and other methods. His work culminated in the 1,500-page chemistry founded on synthesis, organic chemistry founded on synthesis. Berthelot saw this program as a vindication of the unity and identity of forces in the inorganic and the organic worlds. Quote, establishing the identity of forces which act in mineral chemistry with those which act in organic chemistry, by showing that the former suffice for producing all the effects and compounds from which the latter are born. Uniting the organic and inorganic worlds was an essential part of Berthelot's cultural goal of vindicating his opposition to vitalism and his support of a materialist program. So last part of thinking about theory is creating a general chemistry. By the 1850s, organic chemistry had become the dominant subdiscipline of chemistry, but in their quest to answer questions about arrangement and structure, chemists had largely ignored questions about the nature of chemical reactions themselves. Nevertheless, a small number of chemists did research outside the mainstream concerns of composition and structure, studied new analytical techniques such as spectroscopy or links between chemical composition and physical properties. Other chemists were interested in understanding the nature of chemical affinity, why chemical reactions occur the way they do. Since the 18th century, chemists largely had thought about affinity as an attractive force between reacting molecules, a variant of universal gravitation or electrostatic attraction. By mid-century, chemists began to realize that affinity could only be measured indirectly. In the 1850s and 1860s, Julius Thomson and Marcelin Berthelot again independently began extensive research programs looking at the production of heat in chemical reactions. And they concluded independently that the heat evolved in a chemical reaction was an indirect measure of chemical affinity. According to Berthelot and Thomson, chemical reactions produce products that maximize their affinities with a simultaneous release of heat. During the 1880s, interest in affinities and rigorous application of thermodynamics to chemical reactions would come together in the new physical chemistry created and promoted by three young chemists located geographically outside the mainstream of chemical practice. Wilhelm Ostwald was an ethnic German at the Polytechnic in Riga, Latvia. Van 't Hoff was in the Netherlands, and Svante Arrhenius was in Sweden. All three advocated a new physical chemistry based largely on the chemistry of solutions. Ostwald was the ambitious leader of the movement and saw the continual production of new compounds by organic chemists as uninteresting. and wanted to focus on the reactions themselves to create a truly general chemistry that would apply to all chemical reactions. Van 't Hoff followed a reductionist program, striving to mathematize chemistry wherever possible. In 1884, he successfully recast the concept of equilibrium and affinity in terms of thermodynamic principles by defining equilibrium in terms of reaction rates instead of attractions between atoms, and deriving an equation to show the relationship between temperature and equilibrium. In his doctoral dissertation of 1884, Arrhenius drew on established work in electrochemistry and conductivity to create a new theory of solutions in which salts were dissociated into ions. Ostwald was the most active proselytizer for the new chemistry through numerous textbooks and the creation of a large and cosmopolitan research group after his 1887 move to the much larger University of Leipzig. Ostwald attracted students from around the world who would take his principles of general chemistry back to their own countries. Physical chemistry would find its greatest success in the United States. At least 40 Americans studied with Ostwald, many of whom had become disillusioned with organic chemistry and were excited by the allure of an exotic new field that promised to uncover the general laws of chemical reactions. During the 1890s, as American chemists returned from Germany, they established flourishing programs in physical chemistry at universities throughout the United States, many of which began to rival programs in Germany. Among the most significant were laboratories established by Arthur Noyes at MIT, Theodore Richards at Harvard, Wilder Bancroft at Cornell, and Louis Kahlenberg at Wisconsin. The enormous growth of physical chemistry can be attributed in part to the increase in US college enrollments through the 1890s, and courses formerly devoted to analytical chemistry were subsequently converted into courses in general chemistry that emphasized the new physical chemistry. American physical chemists, with their enthusiasm about their ability to teach a truly general chemistry, leapt at these opportunities and at the same time maintaining their research interests in their graduate laboratories. The result was a flourishing physical chemistry community in the United States. So finally, radioactivity. In 1896, Henry Becquerel noticed that uranium salts wrapped in thick paper would create an image of a mineral on photographic plates and left in darkness caused by mysterious rays. In 1897, Marie Curie, an immigrant from Poland trained in Paris, began her famous study of uranium and other minerals that exhibited this new radioactivity, a term she coined in 1898. In the same year, she and her husband Pierre announced after months of arduous labor that uranium ore contained two new elements whose radioactive power was far greater than uranium itself. It's polonium and radium. A bewildering variety of radioactive elements would follow, and untangling the relationships between these two new elements would require a combination of physical methods to quantify the different types of emanations and chemical methods to separate and identify each species. By 1900, the emanations have been separated into three different types, namely alpha, beta, and gamma radiation, and numerous experiments suggested that radioactivity arose from within the atom itself. In 1903, after painstaking examination of a long chain of emanation products, the final what is given here in the bottom, beginning with radium and thorium, Ernest Rutherford and Frederick Soddy at McGill University at Montreal concluded that radioactive atoms were inherently unstable. These atoms emit particles that changed atomic weight and changed it into a new element. So radium became radon, a new gas identified by Rutherford and Soddy. Radon turned into polonium, and polonium turned into lead. Rutherford and Soddy suggested that radium itself must be produced from uranium or thorium because of its short half-life. The Curies and other French physicists were initially skeptical of the transmutation theory as it became known, until Soddy and Ramsay showed conclusively by spectroscopy that the alpha radiation given off by radium bromide consisted of helium. The study of the causes of radioactivity coincided with numerous experiments in physics on the structure of the atom and experiments with cathode ray tubes, most notably J.J. Thomson's discovery of the electron in 1897, led to speculation about subatomic structure. In Rutherford's hands, alpha particles became a useful tool for probing atomic structure. And in a now famous experiment, Rutherford directed alpha particles towards a thin sheet of gold foil, finding that only 1 in 20,000 particles were deflected from their original path. The result led Rutherford to conclude that gold atoms were nearly all empty space, and he suggested that atoms contained a positively charged nucleus that made up only a small fraction of its volume. Two other developments would further redefine the definition of elements. Henry Moseley, working in Rutherford's laboratory, found in 1913 that each element showed a specific correlation between its X-ray emission and a new parameter he called the atomic number. Moseley's number came to replace the atomic weight as the defining characteristic of each element and clarified the exact number of possible elements in the periodic table. Moseley volunteered for service in the British Army at the outbreak of war in 1914 and was tragically killed in the Gallipoli campaign a year later at the age of 27, a loss that deeply affected Rutherford and other scientists. Also in 1913, Soddy had coined the term isotope to refer to the many known radioactive elements that had different atomic weights but identical chemical properties. The fractional atomic weights that had puzzled chemists for so long now had become clear, as they were now seen to become averages of atoms with the same atomic number, but different integral atomic weights. The discovery of the electron subatomic structure would change how chemists thought about the concept of bonding. Although chemists had assumed that atoms were held together in the structure of molecules, they had not attempted seriously to explain precisely what held them together, although they had long been convinced that it was some sort of electrical force. Thomson himself suggested in 1904 that the chemical bond might involve an exchange of a single electron between atoms. With their descriptive and qualitative understanding of molecules, most chemists were at first hesitant to follow Thomson's lead and create electronic models of bonding, although tentative theories began to appear in chemistry textbooks as early as 1904. All early models of bonding assumed a complete transfer of a single electron from one atom to another, resulting in a simple electrostatic attraction between atoms in all molecules, a model that dominated chemists' discussion of bonding until 1916, when Gilbert Lewis published his first paper on the electron pair bond. It actually dates earlier than that, but it was published in 1916. As Lewis further developed his model, it would become to dominate chemists' concept of bonding for the remainder of the 20th century, and even today, of course. Okay, so the last topic here is just in chemical industry, and this is much shorter than the other. So during the first half of the 19th century, the chemical industry was dominated by the production of soda, driven by the increased demand for bleached textiles, glass, and paper, using the process developed by Nicolas Leblanc in 1791. Driven by its large textile industry, Britain dominated the alkali industry in Europe, where whole towns would grow under the shadow of chimneys of large alkali factories. The Leblanc process was very inefficient, as the final product was only 15% of the weight of the starting materials, and the process had an appalling effect on workers and the environment. It released large quantities of gaseous hydrochloric acid in the atmosphere, contaminated productive farmland with solid waste, and the harsh conditions of working with sulfuric and hydrochloric acid created extremely hazardous conditions for workers. The Leblanc process would soon be challenged by the alternative method developed by the Belgian Ernest Solvay in the 1860s that proved far more efficient than the Leblanc process, with far less waste to produce alkali continuously rather than inefficiently in batches. By the 1880s, production of soda by Solvay's method matched that produced by the Leblanc method, and by the turn of the century, the Leblanc process had disappeared. The large-scale production of inorganic chemicals would be joined by a rapidly growing new sector of the chemical industry that produced dyes and pharmaceuticals derived from organic compounds. The extraction of dyes from natural materials, madder root and indigo, for example, had long been large and extremely lucrative industries. But from the mid-19th century, chemists began to develop an increasing number of artificial dyes made from carbon-based compounds. And the key to these new dyes would be coal tar, a liquid byproduct of feeding coal to produce coke for steel mills and coal gas for lighting. Coal tar was largely a noxious waste product with few uses until the 1850s, when it became a starting material producing many new organic compounds. One of the first dyes derived from coal tar was the bright yellow compound picric acid, made by nitrating phenol. But the real breakthrough in the coal tar industry was a much more complex organic compound, a rich purple dye made by Hofmann student William Henry Perkin, who produced it accidentally in a failed attempt to make the antimalarial drug quinine from aniline. After modifying his initial synthesis to produce mauve on a large scale, he brought the dye to market by 1859. His mauve was a sensation, worn in dresses by both Eugenie Bonaparte and Queen Victoria, making it highly desirable color and a fortune for Perkin and his family. Perkin's mauve was one of many new artificial colors that appeared in the 1860s, known as the aniline dyes. Among the most popular was magenta, a red color created by Francois Vergine in Lyon, and aniline blue. It was magenta in particular that sparked an initial explosion in the number of coal tar dye company startups. And the lucrative nature of aniline dyes resulted in the formation of new chemical firms all over Europe. The earliest successful firms were founded in Britain and France, but they were soon overtaken by a number of German firms, and I have a list of 4 of them here. All of these aniline dyes could be made on an industrial scale, but they were initially discovered in a haphazard, accidental way until the 1860s, when the new structural theory of organic chemistry guided chemists in the replication of natural dyes and creating new ones. In 1868, Karl Grebe and Karl Liebermann succeeded in making alizarin, the red compound found in madder root, from anthracene, another coal tar derivative. A modified synthesis of alizarin at BASF would prove to be extremely successful, competing with madder cultivation as the principal source of alizarin. In 1880, Adolf von Baeyer succeeded in making synthetic indigo in the laboratory. His process was eventually improved for large-scale production of indigo. By 1897, the cost of synthetic indigo dropped to less than natural indigo, leading to the eventual collapse of the large British-controlled indigo plantations in India. The growing power of chemists' control over nature would also become evident in the azo dyes derived from coal tar. First discovered in 1858 by Peter Gries, the first 2 azo dyes appeared on the market in 1863, but in 1876, Gries was able to make a wide variety of colors by subtly varying the structure of the starting compound. And the German chemist Otto Witt established a specific relationship between the structure of azo dye molecule and its color. Chemists could now go beyond nature and produce almost any color they desired. And by 1912, azo dyes would make up nearly half the synthetic dyes on the market. German chemical firms were best able to exploit this new chemistry, and by 1878, produced 60% of all global dyestuffs, a percentage that would increase further over the next 20 years, eclipsing dye production elsewhere in Europe and North America. German firms incorporated research and development into their corporate plans, although the path by which this took place was somewhat unplanned and haphazard. A decisive turning point for the development of dyes appears to be the German patent law of 1877 that provided an incentive to create new dyes rather than simply making production costs for existing dyes more efficient. And corporate management began taking active steps towards creating research laboratories that would actively recruit academic chemists to direct the laboratories. All these industrial laboratories were modeled after existing academic research laboratories, although they were somewhat more crowded and less elaborate. The success of these firms relied on actively developing markets by creating a demand for new colors. And the new expensive dyes played a role in the democratization of fashion in the 19th century. Until this time, natural dyes were expensive, making colorful clothes affordable only to the prosperous. Lower class women were able to afford only plain clothing with dull colors or secondhand out-of-fashion recut clothing. During the last half of the 19th century, a number of innovations made fashionable clothing more broadly available, including the mass production of textile materials, treadle sewing machines, printed paper patterns for sewing clothing, fashion machines, fashion magazines that often provided paper patterns, and department stores that were licensed to make copies of the most popular designs using fabrics they also sold in-house. While all of these factors were significant, the new synthetic dyes also played an important role. The patterns for expensive clothing might be difficult to replicate, but colors provided an easy way to make articles of clothing stand out. Colors could also be changed quickly to create a cyclical demand. The new dyes were inexpensive, making dyed fabrics more available and affordable, increasing their popularity among all the classes. Although I don't have time to discuss it completely, the construction and consumer industries would be radically transformed by improved methods for creating large quantities of high-quality steel and aluminum. The Bessemer and Gilchrist-Thomas processes improved the quality of steel and the ability to make it from low-grade iron ore. In 1886, the American Charles Martin Hall developed a method for the electrochemical production of metallic aluminum. As an abundant and lightweight but strong metal, aluminum would eventually find innumerable industrial and household applications, and Hall's commercialization of the process would lead to the formation of the Aluminum Company of America, or Alcoa. It's the largest aluminum manufacturer in the world. Okay, some conclusions to end here. During the 19th century, chemists established sophisticated cultures of intellectual inquiry and professional discipline formation. They established the fundamental ideas of modern chemistry that it would endure throughout the 20th century: atomism, periodicity, structure, bonding, equilibrium. Like their counterparts in physics and biology, 19th century chemists were preoccupied with unification. Chemists were convinced that organic and inorganic chemistry should follow the same natural laws. that analogical reasoning from the organic to the inorganic realms, or vice versa, could help to determine rational formulas. The extraordinarily diverse number of organic compounds could be brought under the general umbrella of chemical structure. The pervading interest in organic synthesis, including Böhler synthesis of urea, Kolbe synthesis of acetic acid, and Berthelot syntheses, reflected the desire to show that inorganic and organic compounds followed the same chemical laws. All the known elements, those discovered after 1869, could be placed in the periodic table that could be explained by increasing the refined electronic structure of the atom and the concept of isotopy. Later in the century, am I out of time?
Yes, that's fine. Are you finished now, Peter?
I'm just about done. I'm on the last page.
Yeah. Okay, thank you very much, Peter, for that absolutely splendid survey of the...
Okay. I had a little bit more to go, but if I'm out of time, that's fine.
Okay.
Anyway, so large number, let's finish. We're at 2 paragraphs left. The large number of new chemists would find careers in the burgeoning chemical industry, which by 1914 had been transformed in numerous ways. The production of inexpensive steel and aluminum made possible the growth of transportation networks, industrial machinery, and consumer goods. The new dye industry, spurred by the success of the structure theory, inaugurated the modern chemical industry and science-based research and development laboratory, simultaneously creating and meeting the demand for fine chemicals and products for consumers. The growth and competition in the dye industry resulted from implementation of robust patent laws and fierce competition between chemical firms in Germany. The emergence of the fine chemical industries, together with the emerging electrical industry of the late 19th century, would lead to the material wealth of the modern world. All three of these cultural trends, theoretical, social, industrial, have clear turning points between 1850 and 1870, when the features of structural chemistry, the production of alkali, dyes, and metals, the means of training chemists, all started to coalesce into their modern form. By 1914, all the components and trends that would characterize chemistry in the modern age were in place. Chemists of the 19th century had created the culture and methods for mass production of many things: chemicals, chemists, ideas, subdisciplines that would be carried into the 20th century, when this mass production would accelerate exponentially as the demand for industrial chemicals, consumer goods, chemists, and specializations continued to increase. Thank you very much, and I'll be glad to take any questions through Peter, I guess. So.
Sorry about that, Peter. Thank you very much for an absolutely splendid survey of the tremendously important period in the history of chemistry. And to be able to do it all in 55 minutes is an incredible achievement. So you deserve our warm congratulations for that. Somebody asked, in fact, it's about the only question we've really got, but somebody asked, has this been published anywhere? Well, of course, this is based on the introduction to the volume you edited in the Cultural History of Chemistry. Another shout out here for the Cultural History of Chemistry. Tremendously expensive ways into the volume to remain it. But I think Peter is reaching over.
It's chapter 1 of this book.
I'm not quite sure how
the introduction to the cultural history of 19th century.
Yeah, so anyway, so it's in that particular volume. It's not available yet as a single volume, nor is it available yet online, but look out for it. It will be available eventually. So,
and the remaining chapters in the book also will go into a lot more depth on the other things that I've mentioned. This was more, my introduction is more of an overview of things to come in the other chapters. So the entire book covers a lot of these things in depth and more. There's a lot of really interesting story of the cultural and popular history of radiochemistry and radioactivity that I couldn't even get to. That's really quite interesting in this period, the early part of the 20th century. So that's in the introduction, but I had to cut it for time. So.
Okay, well, thank you very much, Peter. So I could just remind everybody that next month we're going to have a very interesting talk, not a particularly historical talk, but a very interesting talk by Eva Birdstock, who is at the Professor of Conservation at the Courtauld Institute in London. She's going to be talking to us about the science and technology behind the conservation of paintings. And I know there's a great interest in this group in the history of pigments. So I do urge you to come and hear Eva next month on the 3rd Tuesday of the month. Now, on the 4th Tuesday of the month in June, we have Peter Ramberg again, because Peter Ramberg is going to return to us to talk about how chemistry became the central science. We all have this idea, but chemistry is the central science. That's what makes it important. Peter's going to tell us how this came about. So,
no surprise, it was in the 19th century.
That's right, in the 19th century, yes, of course. We have 41 people today. That's an absolute 42, I think, at one point. Then that's an absolutely splendid number. And I hope that all of you will come back next month to hear part 2, as it were, of this exploration of 19th century chemistry by Peter Ramberg, who is such an expert in this field. So thank you again, Peter, for talking to us all the way from Missouri, and they said Kansas there, from Missouri. Thank you everybody for coming. As I say, 42 people, absolutely splendid turnout. Let's try and do the same next month. In the meantime, have a wonderful time, and if you're British, enjoy the Platinum Jubilee weekend. So anyway, for now, goodbye. Goodbye everybody.